Okay, we'll now talk about section 9.2, which is doing hypothesis tests with proportions. So it's going to be a one proportion z-test. That is going to be the what we are going to do, and doing the same acronym with that. We're also going to talk about type 1 and type 2 error, calculating them by hand. Anyway, so let's look at this. We have a couple of contexts we're going to look at and do a couple of tests. So anyway, so it says here, a worker at a health department of a county in a southern state is researching health issues in her county. In particular, she wishes to know the proportion. So that is the dead giveaway there, that we're dealing with a proportion, not a mean. So we're going to do a z-test. If it had said a mean of something with quantitative data, then we'd be doing a t-test, but that's section 3. So this is a z-test with a proportion. The proportion of adults in her county that eat at least 5 servings of fruit or vegetable each day has changed in the past year after an outreach program had been instituted. A year ago, 34% said that they ate at least 5 servings of fruit or vegetables a day. This year, she takes an SRS of 250 of them, so we'd certainly circle that, in her county, and finds that 102 of them. So let me just go ahead and write the p-hat. So our p-hat, our sample value, is going to be 102 out of 250, and that, in fact, is equal to 0.408, okay, 40.8%. Eat at least 5 servings of fruit and vegetable a day. Does it appear the outreach program was effective in increasing this proportion? So we are suspecting that it has increased. And so the premise of what is being asked here is, and it says perform a test of significance, otherwise known as a hypothesis test, is our sample shows 40.8%, whereas it was 34%. So the sample is certainly more, but is it statistically significantly more? Or is it plausible that that difference of 6.8% is due to sampling variability? So that is, in essence, the question we are going to try to answer here. And so we're asked to perform a test of significance. Whenever you're asked to perform a test of significance, you're expected to write down 5 things. And they spell out the THAME acronym, T-H-A-M-E. And so let's look at that. The T is the type of inference. The type of inference. And so you could actually show this by name or by formula, but we'll do it by name. And so this is what is known as a one proportion z-test. You have to say those words one way or another. One proportion z-test. There you go. You get credit, 1/5 credit if you can do that. The next thing in a test, which you don't have to do when you're making an interval, is write down your hypotheses. Write down your hypotheses, making sure to define any parameter that is there. And so our null hypothesis is going to be the status quo, or whatever is claimed and true. And our status quo here is 34%, is that P is equal to 0.34. Now, our alternative, which is this notation here, H sub A, is what we suspect might be true. And in this case, we're expected that it's increased, so we're suspecting that it's 0.34. By the way, you have to have some reason to go greater than, aside from looking at the sample. You cannot look at your sample data and say, oh, the sample was more, so therefore I'm going to go greater than. You can't do that, okay? So in essence, your hypotheses are occurring before the sample is occurring. Now, the other thing is, if it didn't say increasing or decreasing, now if it said decreasing, obviously this would be less than, all right? But if it just said, is it different? Or if it didn't say increasing or decreasing, which way should I go? In this case, you would go not equal to. That is what we call a two-sided test, where we're going to find our p-value looking for both the greater than and the less than. All right, so then we have 2 tails on it. So, but here it's a one-tailed test, just greater than. Now, we've written p. You have to define your p, or in the next section, mu. P is the proportion. You're always going to say p is the proportion, or mu is the mean. So p is the proportion of all the adults in the county that eat at least, using the wording in the problem, 5 servings. It's a bit cumbersome, I know, but it is what it is. 5 servings of fruit or vegetable a day. So it's a bit cumbersome, but it's what we have to do. It's important that you define any parameter there. There's your hypotheses. So the next part is your assumptions, just very similar to what we did in regards to the intervals, and you must verify them. In other words, you must state whether or not you think it's true in this problem. They're otherwise known as the conditions, verifying your conditions. And it will spell out the SYN acronym. The SYN acronym, just like the last chapter, is it an SRS or random? SRS or random. And so you would say this, it says SRS. It says, and SRS was taken. Thus, random condition is met. Random condition is met. If it didn't say SRS or random, you would say that condition is not met. All right. Then we have the I, which is independence. Is our population size at least 10 times our sample size? So in this case, our sample size is 250. So you would say this: there must be at least 250 adults in the county. No, 2,500. Sorry, there's 250 in the sample, so there's got to be 2,500. There must be at least 2,500 adults in the county for our population size to be at least 10 times our sample size. And so you can just write it like that. And then lastly, normality. Is our sampling distribution approximately normal? And so our little thing there is n times p, and n times 1 minus p had to be greater than or equal to 10. Now we don't know p, but we have a hypothesized value for p, which is 0.34. We're not going to use p hat. When we did an interval, we used p hat. But now we're doing this whole thing here assuming the null is true. The logic here is assume the null is true and that p is 0.34. If we assume that, what's the probability we get a sample value this big or bigger? And so anyway, so this is known as P naught. P naught is the hypothesized value for P. We don't know what P is, nor will we ever know until we do a census, which we're not doing. So we use P hat, the hypothesized value. So this would be 250 times 0.34, and then 250 times 1 minus that, which would be 0.66, and let's see what those numbers are. And so that would be 250 times 0.34. And so that is equal to 85. And then 250 times 0.66, and that's equal to 165. They're both clearly greater than or equal to 10. Thus, normality is met. Normality is met. Saying it more formally, you would say, thus, the sampling distribution of all possible values of p hat is approximately normal. And of course, they will be, assuming the null is true, they'd be centered around 0.34. So how unusual is 0.48? That's what we're going to find out. But we're going to get good data. The assumption or conditions are showing us, hey, you know, we got it random, so that eliminates bias. We have normality, so we feel like we're going to get good, accurate numbers because we've verified our conditions. So the M is the mechanics. And so in this chapter, there's two numbers we have to write in our mechanics. We have to write our test statistic, which is Z in this case, in this section. In the next section with a mean, it'll be T. It's a similar sort of thing. Our little formula on your formula sheet, you can see the formula for test statistic, and test statistic is statistic minus parameter over standard deviation statistic. And standard deviation statistic is this. So in the next section, it'll be that, which will actually be S over the square root of n. But here it's the square root of p times 1 minus p over n. So anyway, our statistic is going to be p hat. Our parameter is p. We don't know p. We're going to use p naught in its place. So let's write that out. And so this would be our p hat minus our hypothesized value over the square root of, and then that'll be p naught times 1 minus p naught over n. Now, you don't have to show this formula, but you could be asked to show it. Now, in general, when you're doing a test of significance, you just have to write the number, what z is, and what the p-value is. But if you could be asked to show your work, in regards to showing the formula, and this is what you would show. So our p hat is 0.408, our p naught, our hypothesized value, is 0.34, over the square root of 0.34 times 0.66 over our sample size of 250. And so that, in fact, is going to be equal to about 2.2697. So what that is telling me is that my sample value is about 2.3 standard deviations from the hypothesized value. And that's probably going to be statistically significant. You recall in a normal curve, when you start getting beyond 2 standard deviations, it starts being unusual. Once you get to 3, it's really unusual. But this, 2.3 is a lot, but the p-value is more exact in that regard. So now we're going to find the p-value. So to find the p-value, this is what we're going to do. We're going to say this. Our reasoning here is this. All right, we have a normal curve for our sampling distribution. It's centered at 0.34. Assuming the null is true, what's the probability we're going to get a sample value of 0.408 or more just by chance? How unusual is this value, assuming that 0.34 is correct? And we'll use normal CDF to follow that. Of course, we could use our tables, but we'll use our calculator here. And so this would be 0.408 to infinity. That's my shaded area. That's my lower bound. That's my upper bound. My mean is 0.34. My standard deviation is the same thing over here, my standard error, which is 0.34 times 0.66 over 250. And that is the mean of my p-hats. That is the sigma of my p-hats. Make sure and label those. And so when you do that with normal CDF, you would get 0.011613. That is our big number, our p-value. And by the way, whenever you label it, don't say p is equal to, say p-value is equal to. You should write it like this, because p is an entirely different thing to us. P is the population proportion. That's our p-value. So, and now we do our ending. Now we do our ending. So all you have to write is what I've circled there, by the way. But this is considered showing your work or explaining it if you were asked to do so. All right. So our ending or our conclusion in context. All right. There's 3 things we have to say. We have to compare our p-value with the stated alpha. There is no stated alpha up in the problem. So we use 5%. We use 0.05. You would say this p-value, and say what it is, 0.011613, is less than 0.05. Okay, that is what we use for our alpha if we aren't given one. Thus, I reject the null hypothesis. And you can write it just like that. You have to connect your p-value with the decision to reject or fail to reject. If it had been greater than 0.05, you would fail to reject. If it's exactly equal to 0.05, you could actually go either way, but they would never give you a problem like that is right on the border, because it'd be confusing in that regard. So if it's greater than, you would say you would fail to reject. If the p-value is low, you reject. If the p-value is high, you fail to reject. You never accept the null. Okay? Then you would say this: thus, I have convincing evidence that, and then you restate the alternative in context. So you're going to, and I know it's a bit cumbersome. It is what it is. I didn't make this stuff up, okay? But, and I don't like the fact that you have to state what P is twice, but I've argued for it, but I haven't won. So anyway, thus we have convincing evidence that P is greater than 0.34, but you have to rewrite what P is again. I apologize for that, but you do. All right. So that P, that the proportion, and you're just going to write out the alternative in words, the proportion of all the adults in the county that eat at least 5 servings of fruit and vegetable, and I'll just use an abbreviation there. That'd be fine. A day is, so all that to define P, is greater than 0.34. Is greater than 0.34. That is how you do it. And that is it. That is our z-test, and those are the steps. So your ending statement has to compare your p-value with the alpha. Do you reject or fail to reject the null, and do you have convincing evidence for the alternative? So that is, it's the way your book does it, and this way I like it done. And this would in essence give you full credit. So anyway, let's talk about what would happen with a two-sided test. Now that's with a one-sided test. If this had been not equal to, in other words, it didn't say increasing the proportion, if it just said is it different, or if it didn't say, just asked you to do the test, then this would have been, if that was the case, then this would have been P is not equal to 0.34. In other words, we're not just testing for greater than by that much, but for less than by that much. And so what would happen down here is it's not just up here or lower, but it's also this far lower. And so that's what, 6.8% below? So it would also be, if you went down 6.8%, which, 0.34 minus 6% would be 0.28. So I guess that's going to be 0.272 or below. But since this is perfectly symmetrical, it's going to have the same area. So in other words, your p-value would just get multiplied by 2. And so that's going to be what? 0.02 and then, I guess 3226. All right? And so it would double. Now, it wouldn't change the outcome in this case. But in essence, when you do a two-sided test, you've got to multiply that value by 2. Now, having said all of that, let me show you the shortcut with your calculator. You do need to be able to perform that, but here's your shortcut. So to figure out your test statistic and p-value quickly with your calculator, we are going to do a one proportion z-test with your calculator. So here we go. So we would go stat, and we would go test, and we go down to one proportion z-test, the fifth option. So this chapter is all about the fifth option for section 2 and the second option for section 3. So that would be a t-test. And so that will go along. So now we've got 4 inferences after this chapter. We also did course number 8 and t-interval and the 11th one, A, which is one portion z-interval. So we are accumulating stuff. But right now we're doing one proportion z-test. And so we hit enter. And so there we go. Our piece of naught, our hypothesized value in this case is 0.34. Notice you aren't entering your p-hat. Okay, you have to enter your x and your n. Your x is your number of successes, which is 102, and your n is 250. So in the problem, if they had given you p hat and not x, you'd have to multiply that times your n to get x. But anyway, it has to be an integer, 102. So that'd be 102, and then our n is 250. All right, and then here's your alternative. So this line is your alternative two-sided, meaning not equal to. Is it less than or is it greater than? In this case, it was greater than at the beginning, so that's what we'll do. And so then we'll go calculate, and it'll tell us our p-value. Certainly, there's our z-test statistic. There's our p-value. This is one thing I don't like about this calculator. It says p is equal to, but that's not p. It's the p-value. Don't write it as you see it there. Write it like this. Write p-value, not p, because p means something else to us. It is the population proportion. So there you go. That's how to quickly get your test statistic and p-value. Now, by the way, so let's remember that number. Now, let's do if it was a two-sided test. In other words, if it was not equal to. So we'll do stat, test, and go to number 5. And we go to that. Two-sided just is not equal to. Our alternative is not equal to. And if we do a calculate, we'll get the same thing, except now our p-value is doubled. So that's with the two-sided test. Okay, great. So let's get some more practice, why don't we? Okay. Same sort of thing here. And, okay, let's see what this context holds for us. So a researcher wishes to test the hypothesis that 60% of trees in a forest have a particular fungus. He takes a random sample of 320 trees and finds that 210 of them have the fungus. All right, so that would be our p-hat. Our sample p-hat is going to be that 210 out of 320, so 210 is our number of successes, which a success is defined as having a fungus here. And so 210 out of the 320 have the fungus, and so that ends up being about 65%, 0.65625. So certainly more than 60%, but we'll see if it's statistically significantly different. But anyway, perform a two-sided, that means our alternative is going to be not equal to. Also create a 95% confidence interval and comment on how the p-value relates to the interval. So this is a popular question. A lot of times we don't do it till kind of the end of the chapter, but it's good to do it now, is to make the connection between Chapter 8 and Chapter 9, the connection between an interval and a test. So we're asked to perform a test, so we're going to do the same acronym. So just like what we just did. The first thing we have to state is our type of inference. This is a one proportion z-test. One proportion z-test. So if you can just say that, you're going to get 1/5 of the problem right. Then our assumptions. So our assumptions. So, I'm sorry, I'm going back to interval speak. My bad. The THAME acronym, we have to state our hypotheses. So our hypotheses. Our null hypothesis, in this case, that is the status quo or whatever's claimed as true. Researcher wishes to test that 60%. So P is equal to 0.6, right there. And so our alternative is what we suspect might be true. And so in this case, we just want to see if it's different. It didn't say greater than or less than. It would not be good to look at the sample value and say, oh, that's bigger than that, therefore I'll go greater than. You can't do that. So it's not equal to. We have no reason stated in the problem to test for greater than or less than, so we go not equal to. So that is what a two-sided test is. Okay, I've got to define P. Since I've written P, I've got to define it, unless it had been defined up here, which it wasn't. P is the proportion. So it is the proportion of all the trees. Make sure you say the word all. Okay, and that it's clear that you understand that P is a parameter. It describes all of the trees, in this case, in this forest. Okay, all the trees in this forest that have, the particular fungus, the fungus. There we go. I think that would be clear there. All right, we're 2/5 of the way done. Now, kind of the hardest part is the assumptions, but it's basically the same thing we did in the last chapter. We must verify them, verify the assumptions or the conditions. So we sin. And so we would say, random sample. So we will say this. It says a random sample was taken. Thus, random condition is met. That's the easiest way to say it, so please just say it that way. The results of that is we won't have bias, in essence, in that way, in regards to our selection. Number 2, so that would be the S of the sin, random sample or SRS. All right, then we have the independence. So the independence condition is our population size must be at least 10 times our sample size. So our sample size is 320, so we got to have 3,200 trees at least. There must be at least 3,200 trees in the forest for big N to be greater than or equal to 10 times little n. Our population size at least 10 times the sample size. Sorry, I wrote that kind of off the camera there, but because we're not using replacement. Okay. So and then lastly, as far as our conditions, normality. So in regards to normality, n times p naught in this chapter and n times 1 minus p naught are greater than or equal to 10. So our n is 320 times our p naught. We're doing this whole test assuming the null is true. All right, and so we'll use P naught here. So this would be 320 times 0.4. Let's see what those numbers are. 320 times 0.6 And so that's equal to 192, and then 320 times 0.4. So that is equal to 128. They're both greater than or equal to 10 clearly. So you would say, thus, normality is met. In other words, our sampling distributions of all possible values of p hat will be approximately normal. Thus, normality is met. There you go. That's the quickest way of saying it. As you may have noticed, we're going to be doing this, basically, this similar sort of thing every single time. If you can get good at sinning, at doing this, you're going to do well at, that's a big step in doing well at inference. Wording it properly. Word it like I worded it here. All right, then we have our mechanics. And there's two numbers we have to write in our mechanics for every test, whether it be a z-test in this section, a t-test in the next section, and then the next chapter we'll do more z-tests and t-tests, and then the chapter after that we'll do a chi-squared test. Okay? But we have to write our test statistic p-value. So we will use those. I just showed you how to do them by hand in the last section, so I won't do that here. I'll just do it. All you have to do is write the numbers. So you do have to understand what I did in the last problem in regards to using the formula and using normal CDF. But in general, you can just do this to write the numbers. So we'll go to stat test, and go down to number 5, one proportion z-test. And so our hypothesized value is 0.6. And our sample number of success is 210. Don't put a decimal there. Don't put your p-hat, please. And so sample size, your number of successes can't be bigger than your sample size. And we're going with a two-sided test, not just greater than, but also less than as well. And so we go calculate. And so there it is. There they are. So it'll be so our z-test statistic is equal to 2.054 approximately. And then our p-value is that number right there. So it is our p-value is equal to 0.03998. Okay, those are our two big numbers. And so this is the number of standard errors that my sample value is for my hypothesized value. And so that is what that is telling us. The reason we find it is sort of tradition in stats, because test stats are used to calculate p-values. Now, your calculator does it for you, but they're also referenced a lot. Z-scores and T-scores are referenced a lot. And just in general, you just need to remember that, hey, you start getting beyond 2 to 3 standard deviations or standard errors, from the middle, it starts being unusual. And then a p-value. This p-value, what it is, p stands for probability, as we've been talking about. It is the probability that, assuming the null is true, assuming that actually 60% of the trees in the forest have the fungus, the probability that you would randomly select 320 trees and get 210 or more, all right, that have the fungus is that, roughly. And you could also, by the way, use binomial CDF on this as a binomial problem, but we won't talk about that. All right, we're just using normal right now. And that's what, in essence, your calculator is doing. So this is a conditional probability of getting a sample value this unusual, assuming that the null hypothesis is true. So that's what that is. And by the way, that would be explaining, if you were asked to explain a p-value as a probability or to explain a p-value, what it means in context. You would say, well, assuming that 60% of the trees have the fungus, the probability that you would take a sample size 320 and get 210 or more, or that unusual, that this high or that low. In other words, 5.6% above 60% or 5.6% below, because it's two-sided, the probability that that would happen is about 4%. Okay, so that's what a p-value means. But our ending that we have to write here, you don't have to write that here unless you were asked to explain what the p-value means in context. Our ending, in other words, our conclusion in context. So our conclusion in context, and we have to say 3 things in regards to our hypothesis test. First of all, we have to compare the p-value with alpha. Now, and in this case, it didn't give us an alpha, so we use 5%. So you would say this p-value, and say what it is, 0.03998, about 4%, is less than 0.05. Thus, I reject the null hypothesis. If the p-value is low, then you reject the null, okay? You reject the null. And so what that means is, and since we're rejecting that, it means we've got convincing evidence for that. If we don't reject that, it means we don't have convincing evidence for that. So, and we're going to say that in context. So this p-value, thus I reject the null, thus we have convincing evidence that, and you restate the alternative in context, that the proportion of all the trees in this forest that have the fungus is not equal to 0.6. So that is our conclusion, is that the 0.656 is statistically significantly different. All right. Now, the other thing it asks us to do is to create a confidence interval in this situation. So let's do that right quick and connect it with the test. That's an important thing to be able to do. So if we make a 95% confidence interval like we're asked to do up there. And so we'll do that with our calculator. You know, it's going to be p hat plus or minus z star, you know, times our standard error, the square root of p hat times 1 minus p hat over n, well, just like what we did in the last chapter. And I'll do that quickly with the calculator with the z interval. So I'll do stat, test, and I'll go down to option A, which is the 1 proportion z interval. So 1 proportion z interval. Notice it goes ahead and puts the 210 out of 320 in there automatically because I did the test. And I'll do 0.95 because that's what it asked me to do with 95% confidence up in the problem. And so there's my 95% confidence interval for P. And so my 95% confidence interval is 0.60421 to 0.70829. So what we would say in the last chapter, we're 95% confident that P is in here. And so the way that relates to the hypothesis test is this. This hypothesis test is testing 0.6. You'll notice that 0.6 is not a plausible value according to this interval for P. This P is giving the plausible values at 95% confidence, the plausible values for P. This 60% is not plausible. It is not in the interval. So the reasoning of the test is, since it's not in the interval, it should be rejected. And that's what the hypothesis test is saying. The hypothesis test is telling us to reject it. So connecting the interval with the hypothesis test is this, is you would realize values that are not in this interval are not plausible, according to this interval. Okay? This is not a plausible value at 95% confidence. Now, that relationship holds true on a two-sided test when your alpha, and alpha is 5%, which is 0.05 here. We use 0.05 for alpha. These two have to add up to 100%. The 95% confidence interval is related to the two-sided hypothesis test with alpha is 0.05. And so the way you would make the connection is this. You would say the null hypothesis value of P is equal to 0.6 is not in the 95% confidence interval. Thus, it is not plausible. It is not plausible at this level and should be rejected. It doesn't mean it's wrong. It doesn't mean we can say, well, we're 100% sure it's wrong, because everything we're doing here is based on sampling and estimation. It's saying that we're going to reject it. We don't think it's true. It's not a plausible value. It's a possible value. It's just not plausible. And this agrees with the test. This agrees with the test above, because we got a p-value below 0.05. So the relationship there is, if your hypothesized value is not in the interval, that means the p-value of the related test is going to be below the alpha. Whereas if we pick something in the interval, like let's say 0.65 was our hypothesized value, all right, which would be actually really close to our p hat, then you would expect a high p-value because you would not reject it. Okay. Last, now that's really the main kind of logic that is in the chapter and the main thing you have to know. I do want to do this problem. This is something, and some stats classes don't even bother with doing this because this is sort of a difficult problem, but I wanted you to give you the opportunity to be able to do this. So if you want to stop the video now and just not want to hear this, that would actually sort of be fine. But this is a potential number 6 problem on your free responses. And this is sort of a tough problem. I mean, some people look at it and it sort of makes sense to them, but it's finding the probability of type 1 and type 2 error and the power by hand. And it hasn't been on the exam, but all the different parts of the reason I like doing it is because all the different parts of it have been on the exam, and it sort of forces you to understand a number of different things. And like I said, it is a potential problem in regards to number 6. And so hopefully, let me see if I can explain this to you. And by understanding this, hopefully you'll understand the concept of hypothesis testing more deeply. So calculating the probability of type 1 and type 2 error and the power. And you'll recall from the previous section, remember, whenever I encounter type 1 and type 2 error, I say to myself this: 1 is hot. 1 is hot. And so what that means is, in type 1 error, the null is true. Okay, the null is true, and it's an error, so I must have rejected it. But I rejected it. But I rejected it. And so type 2 error is the vice versa of that. Type 2 error is the null is false. And it's an error, but I failed to reject it. I failed to reject it. We never failed to reject. Let me go ahead and write the null. We either failed to reject the null. Now, what power is this? Power is a type 2 situation where the null is false. So power, I'm running out of space. Power is this. It is a probability. It is when the null is false and I did the right thing, I rejected it. So it is a conditional probability. Power is the probability that given the null is false, that I'm actually going to reject it. The way I think about power is Superman. What does Superman do? All right, Superman, there's bad things that happen, and Superman shows up and he gets rid of the bad things. Power, Superman has power. In other words, we got bad stuff. We got a false null hypothesis. We need to get rid of it. Well, that's what Superman would do, and that's what power does. He rejects it. And so calculating, and it is, by the way, it is always equal to 1 minus the probability of type 2 error, which we're fixing to calculate. And type 1 error, the probability of type 1 error, by the way, is always equal to alpha, as we're going to demonstrate here. So that's an easy calculation that you definitely need to get right. And that'll be a problem in your test. It'll give you a situation, it'll say, what's the probability of type 1 error? Alpha. And it'll stay in the problem. Alpha is equal to 0.05 or alpha is equal to 0.01 or whatever. So make sure and get, that's an easy calculation. Now type 2 error, probably type 2 error and power definitely, it's just not easy, and I'm sorry, but maybe you'll find it to be easy. Your book does a good job of explaining it, and so and we'll certainly work on this in class. But anyway, so here's our situation. It says each day a truckload of potatoes arrives at Milio's potato chip factory. He takes an SRS of 200. Good, that takes care of our bias there. All right. So each day, and finds the proportion that are rotten. So he is interested in the proportion that are rotten. So we know that's section 9.2. It's a proportion. If he has statistically significant evidence that alpha is equal to 0.05, we can go ahead and say the probability of type 1 error is 0.05. If we know we're going to get that problem right. All right. If he has statistically significant evidence that more than 15% are rotten, he'll reject the whole truckload. What values of the sample proportion would cause you to reject the truckload? Now, what we're going to do here, our null hypothesis is going to be this. our null hypothesis of our test is just going to be P is equal to 0.15. Our alternative is what we suspect might be true. Or what would call for a change, or what would cause a problem, what would be a big deal. In this case, if we have evidence that P, the proportion of rotten potatoes, is greater than 0.15. So this is what we're testing. So this is, in order to calculate the probability of type 2 error, in order to show what this is, we would have to think about our old friend, the sampling distribution. Assuming the null is true, and that it actually is equal to 15%, all the possible values of p hat, which are in here, of my sample proportion, they're going to be centered around p hat, okay? Most of them would be pretty close to it. Some would be out. But if our sample proportion gets way out here, okay, gets too far out in the tail, we're going to reject it. The question is, what is this value of p hat that would be so far greater than, we're going greater than because our alternative is greater than, that would cause us to reject it? How far out do we have to go? That is what the alpha value that's what it establishes. It establishes how far out in your curve you're going. An alpha value of 0.05 is basically saying if you get a p-value below this, all right, you're going to reject the null. And so this alpha value is 0.05. Alpha is the area of my curve that I am rejecting. A p-value is in essence an area of a curve that we're going to get with normal CDF. Anything below 0.05, any p hat that's over here, I'm going to reject. And so what is this value here? Alpha establishes the percent of my curve that I'm rejecting. Now, of course, if this had been a two-sided test, I'd have to split the alpha in half, and 2.5%, 2.5%. But how can I find this value given the area? And that's our old buddy inverse norm. I'll do inverse norm, and I'll do left area. If 5% is to the right, that means 95% is to the left, so this would be the left area. Of course, you could do right area with the latest 84s, but anyway, but with most of the old ones, you'd have to do this. Our mean is 0.15, and our standard deviation, just like it has been, the square root of p times 1 minus p over n, so 0.85 over 200 is our sample size. That gives us 0.19153. So that is this value here. Any sample value I get above that, it would cause me to reject the whole truckload. So this is creating what is known as my rejection region, which is actually a method of hypothesis testing that we don't really do, but it is a plausible thing to do. And this is not my acceptance regions. We never accept. This is my fail to reject. This is my fail to reject region. So any p hat that we get that's over here, we fail to reject. Like let's say if I got 18%. I'd say, well, in my sample, I got 18% rotten potatoes, but it's 15% is still plausible. It's in my fail to reject region. But if I get 21%, let's say, that would cause me to reject the 15% claim because it's too high. It's not plausible that it's due to sampling variability at this level. Now, and think about this type 1 error sort of thing. This situation is we're assuming the null is true. We're assuming that this truckload really did come into with 15%. And all these differences are happening due to sampling variability. We took a sample size 200 and get a p hat. Well, what happens if just by chance we get one of these p hats over here? And let's just say the null really is true. Well, just that is, and so that is that would be type 1 error. The null is true, and I just rejected the truckload. I rejected a good truckload of potatoes, in essence, just because of sampling variability. So hopefully, that will lead you to a better understanding of type 1 error. But all that to say, what values would cause you to reject the truckload if my p hat was greater than 0.19153? Anything greater than that, and I'm rejecting it. All right, here we go. So unbeknownst to Milio, a truckload arrives that has 22% rotten potatoes. So unbeknownst to him, we have a false null hypothesis, okay? Meaning we have a potential type 2 error situation. potential type 2 error situation. Find the probabilities of type 1 error. So I'm going to draw, in essence, if in fact the truckload really does have 22%, well, that's 19%. So 22% is going to be about right here. This is actually going to be the true distribution. See, all Emilio knows is that he's going to weigh, or he's going to check out 200 potatoes, and if he gets more than 19.15% that are rotten, he rejects them. Okay? But the problem is, here's a bad truckload that is centered at 0.22. Okay? And more than likely, when Emilio takes his sample, he's going to get a p-hat that's up here around 0.22, which is going to be greater than 0.19, and thus he would reject this bad truckload there. Okay? But the problem is the overlap here. Okay? What happens if he got, from this curve, he got a p-hat over here? That falls in his fail to reject region. Let's say just by chance with this bad truckload, he gets like 18% rotten ones. The problem is he would fail to reject a bad truckload, and that is type 2 error. So this overlap, type 2 error, another way of thinking it, it's the overlap of the two curves, in essence centered around my reject and my fail to reject region. So this area here, which I'll make this little striped area there, that represents the probability of type 2 error. And then this other area over here, which I will put little horizontal stripes for it, I guess, that is the probability that I'm going to reject this bad truckload given that our null is false. And that is what we call power. It is the conditional probability. So how can I find this area for power? Our old friend normal CDF. So in regards to power, we would say this. We would say normal CDF and then this would be 0.19153, and our sample size cannot change. That is my lower bound. My upper bound is just infinity, or you can just put just a big number. And then my new mean, the mean of this curve is 0.22, and the standard deviation is the square root of 0.22 times 1 minus that, which would be 0.78 over 200. And when that is my upper bound, that is the mean of my p-hats. That is the standard deviation of my p-hats, properly labeling. And this is equal to 0.8345. That is my power. That is the probability in this situation, assuming that the null is false, that I would reject it. And that's what power is. And then the probability of type 2 error, in other words, that assuming the null is false, what's the probability that I fail to reject it? That is this area there. It is always 1 minus the power, which is 0.8345. And so that is equal to 0.16554 right there. So that is how you calculate them by hand. Now, but what's especially important is understanding, like I said, the probability of type 1 error is always equal to alpha, and understanding that, that power is 1 minus the probability of type 2 error, and vice versa. So anyway, we'll be talking more about that in class and about examples of explaining type 1 and type 2 error in class, type 2 error in class and power. So thank you for paying attention. I wish you the best in regards to one proportion z-tests and calculating the probability of type 1 and type 2 error in power.